Okay, so we're talking about distance between a variety of different things, lines, points, and planes. So I'm just going to go over some brief examples today. If you know how to calculate magnitudes, dot product, and cross product, you can do this, okay? So the idea is that when I'm trying to find the distance between two things in 3 space, or in 2 space, we will find a vector that connects a point on each element, let's say. So element meaning like the line and the plane, or the point and the plane. I mean, I don't have to find a point on a point, but you get the idea. And what I really want, when we think about the shortest distance between two things, let's just say I draw a line here and a point. How could we measure the shortest distance between these things? Mark? Yeah, so the perpendicular distance, I think we talked about this like in a grade 10 or 9 course, but the shortest distance is the perpendicular distance. So the idea is that if we can find a mutually perpendicular vector to each element, of course a vector can't be perpendicular to a point, but if it's a point in a line or a point in the plane, I want a normal vector to that line and plane. If it's 2 lines, I want a vector that's mutually perpendicular to both of those things. And then we'll find the magnitude of the projection of a vector connecting 2 points onto that mutual normal. Okay, so if I know another point over here on this line, let's say, I will find, so this is going to be like my normal, let's say, my normal to my line. I will find the projection of this onto the normal to find the distance between those 2 points. Yeah, so formula. We are actually using the projection formula. So the distance formula is going to be given to us by the vector that connects 2 points being projected onto the normal. And just to kind of unpack the magnitude formula for you guys, this is the same as the magnitude formula that we learned before. We do the dot product of those 2 things. We take the absolute value of it because we want to get a positive for distance. And then I find the magnitude of that normal vector. Okay, so n, vector n, I actually edited this and I feel like it didn't save. Okay, well, hopefully everything's saved. N is going to be that mutually perpendicular vector that we talked about. And then our vector P1, P2 is a vector connecting a point from each thing. So a point from each line, or a point from each plane, or a point on the plane, or whatever. Okay, so really guys, this is just a review of how we find magnitudes of projections. So P1 and P2 are going to be a point on each element that you're trying to find the distance between. So if I'm trying to find the distance between a line and a plane, I need a point from the line and a point from the plane. Okay, there's a couple little exceptions to this because this works for the most part, but if I happen to have like 2 parallel lines, it can be difficult for me to find that mutually perpendicular vector because I can't cross the direction vectors. And in that case, we're going to need kind of something slightly altered from this projection formula in order to find the distance between those 2 things. So there's a couple little things that I'll show you on the next slide that are exceptions to this. Can I flip or no? We're all ready? Okay, so for a point and a line in 3 space, or 2 parallel lines in 3 space, we're going to use this different formula. So if we think about this flat image that I showed you here, it's pretty easy just to think about how we can find the normal to that and find 2 points and then use the projection. But as soon as it's in 3 space, that becomes a little bit more difficult because I can find literally any normal along this, a line in 3 space, whereas in 2 space, my normal to my line is always going to be flat. along that line. But as soon as I have a line in 3 space, I could literally have a normal like anywhere around this. So what's the proper normal to use, right? That's really hard. Like that would be a really challenging thing to decide. So what we're going to use, and I'm going to explain this formula to you, is we'll still use the P1, P2 vector. So we'll find a point, let's say it's 2 parallel lines in 3 space. We'll find a point on each line. We'll find the vector that connects them. And then what I'm actually going to do is cross that with the direction vector to the line and divide it by the magnitude of the direction vector. Okay, so our P1, P2 is going to be a vector that connects the 2 points, and D is the direction vector of the line. If you have 2 lines that are parallel, it will be the same direction vector. So there's no confusion as to what direction vector we use. We're just using the direction vector of the line, either for the point and the line or the 2 lines. Okay, and leave yourself a little bit of space at the bottom because I'm going to explain to you why we use this. Okay, so the question is, why do we change the formula of the projection around? I think the answer to that is what I explained to you before, and that is that a line in 3 space can have like infinite normals to it, and then we don't exactly know what normal actually reaches out to the other line or reaches out to that specific point. But also, we come up with this formula because of area of a parallelogram. So I'm going to show you distance calculated in 2 kind of different ways. And it actually is what makes this formula work. Okay? And I'm not finding the area of the parallelogram or anything like that, but technically when I do the magnitude of the cross product, or the, I guess this is magnitude of the cross product, I am actually calculating the area of a parallelogram. So I'm just going to kind of show you guys why this is equal to distance. Okay, so let's suppose I'll use the example of the point and the line in 3 space, so distance from a point to a line, but it's very similar for the 2 lines as well. So let's say we have some line in 3 space. Of course, I'm drawing this as a 2D line, but that's okay. So we have some line, and that line has a direction vector, right? Every line has to have a direction vector. So let's just say this is our direction vector, right? Vector D. And then I have some point somewhere in 3 space, and it goes out, maybe it's over here, right? So the shortest distance we know from this point to this line is this distance right here. That would be the distance that I would want to find, because that's the perpendicular distance. So we'll just call this like our distance line. That's kind of like what we're aiming to find. Let's suppose that we have some point over here. So maybe we can call this P1. And this is our point number 2 that we're trying to find the distance out. So remember, we always need this P1, P2 vector in our formula. So just a point on each element that's connected and creating a vector here. So this is our vector P1, P2. Okay, so look at what I'm doing in the above formula. I'm actually crossing P1, P2, vector P1, P2 with the direction vector. And that means that what I'm actually doing is I'm finding the area of the parallelogram that connects kind of those 2 vectors when they're arranged tail to tail, right? So here's my area of my parallelogram. So in one sense, the area of my parallelogram we know is the 2 vectors arranged tail to tail being crossed, and then I find the magnitude of that. So that's one way that we can express area of a parallelogram. Now, we know just from our studies, our previous studies, that area of a parallelogram can also be expressed by just doing base times height, right? So imagine I slide our distance vector over here. or our distance line over here. I guess it's not really a vector. I'm going to just label this on the other side. Okay, so I just slid our distance vector over here. So another way that I can also express area of a parallelogram is base times height. Agreed? Like it's the same thing as like area of a rectangle or area of a square, base times height. So here, if we think about our base, my base is actually the magnitude of my distance or my direction vector. Okay, this is the green part. That's going to be the length of my base of this parallelogram. Okay, this length right here. And my height of this parallelogram is actually that distance vector that we just talked about, right? So it's times our distance vector. So when I set these two things equal to one another, okay, I don't actually want to find area of a parallelogram, but area of a parallelogram is what actually makes this work so that I can isolate for the distance vector, right? So I know that this and this must be equal because they're both equal to the area of the parallelogram. So if I say that my magnitude of my distance, my direction vector times my distance is actually equal to the magnitude of the cross product of P1, P2 and the direction vector, I can actually isolate for that distance portion by dividing out the magnitude of the direction vector. So if I divide that out, I actually get that formula that we worked with above. Okay, and that's why this formula actually works to give me the distance between those two things. So this is distance, right? Devin?
Are we going to have to prove this on anything?
No, I just want you guys to know why it works, where it comes from. Okay, so if that didn't make sense to you, it's totally okay. I just wanted you guys, just didn't want you to think that I was throwing a random formula at you and that it didn't have any connection to anything else. Zainab? This is part of the last unit. Okay, so we get our formula above. So we're going to use this. If you have a point and a line in 3 space, we're going to use this. And then if you have 2 parallel lines in 3 space, you can also use this. Otherwise, we will defer to using this formula here. So we find the normal, dot it with the P1, P2 vector, and then find the projection. Okay, so let's try it out. So find the distance between the point P and the line 2x plus 5y minus 9. So 2 space or 3 space? 2 space. So we can easily find the normal of this line. What's the normal of the line?
5 minus 2?
Nope.
3, 4.
Nope. Normal of the line.
Oh, it's 2, 5. Oh.
Yeah. It's the vector 2, 5. Scalar equation gives us the normal, right? So that's the nice thing is that we already have the normal vector. I don't need this mutually perpendicular vector because I can't find a perpendicular vector to a point. But I do need to connect this point 4, -3 to a point on my line. So I need a point on the line in order to find that P1, P2 vector. Yep. So I need to plug something in for x and y here that make this left side equal to 0. If I get a true statement, that means that I've found an x and a y coordinate that lie on that line. Any ideas for how we can do this? 2 and 1? Does that work? Okay. Lovely. So therefore, 0 equals 0, and 2, 1 is a point on the line. So now that I have that, I can find my P1, P2 vector. it doesn't matter the order in which you do this. So let's just say we call this P1 and we'll call this guy P2. So the point that I'm given, I'm going to make that P1. And the point I just found, I'll make that P2. Again, shouldn't really matter either way. So I'll do the P2 components minus the P1 components, meaning I'm getting the vector -2 and +4.
For the P2, like, did we just make that up?
So it has to fit, it has to make this a true statement.
Yeah, but
Yeah.
like, yeah.
So yes, you make it up. -3 is also a point that could have worked for this. Okay, now I'm just going to plug it into that formula. So we're just going to do the projection of P1, P2 onto the normal vector. Lauren?
Where did you -2, 4 come from?
So I'm doing 2 minus 4 and 1 minus -3 here. So P2 components minus P1 components. So we'll use our distance formula. And that's going to be the magnitude of the projection of P1, P2 onto that normal vector. Okay, so we have to do the absolute value of P1 dotted with the normal vector, and then I do the magnitude of, divided by the magnitude of the normal vector. Okay, so this is good review of Unit 2 here, finding projections. So P1, P2, vector P1, P2 dotted with the normal vector, I'm going to get the x components multiplied, added with the y components multiplied. And in case that's negative, we want to take the absolute value of that. And then the magnitude of my normal vector is each component squared and added. So 2 squared plus 5 squared. Okay, so I'm getting here, this is 20 plus -4, so I got 16, and then root 29 for that bottom. So it's 16 over root 29 units. Okay, we're going to do another one, so if you're a little bit confused, the general process here is find something that's normal to both things. Unless one thing is a point, then you're just going to find the normal to the line or the plane. You need a point on each thing and find the vector that connects them, and then you do your projection. Okay, that's essentially what we want to find. Questions for this one before we move forward? Okay, we're going to try something similar, but it's going to be the distance between the point and a plane here. Okay, so of course, I don't need something that's mutually perpendicular to these because the other thing is just a point, but I do need the normal to the plane. So what normal can we use? Great. So the scalar equation actually gives me the normal to the plane, right? So it's 1, 3, -7. I also need, I have one point, but I need also a point on the plane so we can find a vector P1, P2. So point on the plane, I think maybe the easiest thing that we can do here is just set x equal to -100 and let y and z be 0. And then we know for sure that we have a true statement here. So then we get 0 equals 0. So therefore, -100, 0, 0 is a point on the plane. That's probably just like the easiest thing that we can go for here. Okay, so perhaps we can call point A our P1, and then we can call this our P2. Okay, so we have our normal that we're going to use for our projection. I also need the vector P1, P2, so the vector that connects the point and a point on the plane. So I'm going to do P2 components minus P1 components. That gives me -107, -1, and -21. And I think just for our purposes here, we can just make this the vector in the opposite direction, just so we don't have as many negatives. Because I can do P1, P2, or P2, P1, doesn't really matter. If you want to use the one with the negatives, that's fine. You'll just end up taking the absolute value probably of a negative number when you do P1, P2 dotted with the normal. Sorry, I'm like losing my voice here.
Sorry, how do you get the Z component?
0 minus 21.
Oh.
Am I wrong? Did I do
No,
something wrong?
Never mind.
Oh, okay. Okay, so here's our point that we're going to use, or our vector, sorry. So we're just going to use that distance formula again. So the distance formula, I'll just show you here so you know which one I'm using out of the two. We're doing this again, so same thing we did last time. So we're going to find the absolute value of that dot product between the normal and the position vector that we just found, or the point vector, I guess we can call it. So it'll be 1 times 107, which gives us 107, 3 times 1, and negative 7 times positive 21 will give us negative 87. Is that correct? No,
I got negative 37.
negative 37, yeah.
What?
No, 21 times negative 7.
Guys, pen.
147.
147, there we go.
147?
And then the magnitude of the normal vector, so each component squared and added. Of that normal vector. Okay, and then what are we getting up here? We're getting negative 37, is that right?
But I did the whole thing.
Oh, did you?
So I got negative 37.
Makes sense. So 1 plus 9 plus 49.
50.
Great. And I'm taking the absolute value because we don't ever want to express distance as a negative. So that's why we need that absolute value, because sometimes our dot product gives us like the negative option, and we definitely want to have the positive option there. So this is going to be 37 over root 59 units from the point to the plane. And this gives me the shortest distance from the point to the plane. Okay, questions on this one? We're okay? Okay. Last couple here. We should be getting kind of in a groove here. Distance between two skew lines. So firstly, I know these are not parallel here. If they happen to intersect, you will probably find that your distance, shortest distance between those two lines is 0. So these are two skew lines. I'll just tell you that now. How do I get a mutually perpendicular vector to both of these lines? Anil? So not the S and T, but the direction vectors for those S and Ts. Yes. So we're going to cross the direction vectors to get a mutually perpendicular normal vector. So I'm going to cross 1, 2, 3 with 2, negative 1, 1. Again, order doesn't really matter here. So our normal vector will be 2 minus negative 3, so 5. 6 minus 1, so another 5. And then negative 1 minus 4 gives us negative 5. So you actually can reduce your normal vector So Anil, if you want to try reducing it and see kind of what you get here, I'm not going to reduce it, and then you can see what we'll have to do if we don't reduce it. And then I need my P1, P2. So how can I find my vector P1, P2?
You just use the points.
Yeah, we have a point number 1 and we have a point number 2. Perfect. So I'll just do 2 minus 5, 0 minus negative 4, and 1 minus 2. So I can use that as well. Okay, so now we're just going to do the same thing that we did on all the other questions. We'll find the distance by doing that projection. Okay, so notice I didn't simplify my normal vector. I will show you, if you happen to simplify your normal vector, I'll show you kind of how we end up at the same place. Okay, so we'll do absolute value of negative 15 plus 20 plus 5. And then down here we're getting 25 plus 25 plus 25. So I'm just squaring each component here in the normal vector. So this just gives us 10 over 75. And then your job from here, if you didn't reduce the normal vector to start, is actually just to reduce the rational, or the radical. So 75, how can I express this as a simple radical, like simplest radical form?
2 over 3.
Just the 75 I'm interested in for now. So what's the biggest perfect square inside of 75? 25, right? And then we root it and we get 5. So this is actually equal to 5 root 3. And then you'll notice that the 10 and the 5 reduce to 2 over root 3. So if you happen to take the route where you reduce the normal, you should see here that you get the same answer that we got.
Don't you not like those in the bottom though?
Yeah, so we can write this as 2 root 3 over 3 as a final, but I won't be too picky about that right now. Okay, so to get from here to here, I was splitting 75 up into 25 times 3, and then I took the square root of 25 to get 5.
I've never do that in these yet. I can't do that.
Or you can just reduce the normal, and then it'll be all reduced for you.
That's what I did, but it still gives 2 root 3, 2 over root 3.
Yeah.
So I have to rationalize it.
Yeah, right. Okay, proper form, again, would be like 2 root 3 over 3 as the rationalized denominator.
So we have to rationalize
Just remember,
When it comes to
like, if she writes it on the
exam,
board, just like
Yeah.
check.
I'll ask for it in simplest form for sure. Like you need to be able to go from here to here for sure.
Oh, so you don't have to radical on these?
Yeah.
And then I just feel so good. Then when I get the
Rationalize.
You don't have to radical on the exam.
Oh my god, I'm so not.
I don't know. I'll let you know when I decide. Okay, last one. And then we'll have some time to work today. I told you it would be short today. Find the distance between a point and a line in 3 space. So this is actually an example of the second formula that I gave you. So in order to do the second formula, this is actually like almost slightly easier because you don't have to really find anything. You're just going to find a point on your line and find the vector that connects that point and the point on your line. Cross it with your direction vector of your line, and then find the magnitude of each of those things. So you're going to divide it by the magnitude of your direction vector. So here's what I need. Well, actually, I already have a point on my line. So here we can say maybe this will be P1 and P2. This is going to be our direction vector. And all I need to find here is the vector that connects P1 and P2. And then I can just plug right into that formula. Okay, so we'll do 1 minus negative 1, giving us 2. 2 minus 1, giving us 1. And negative 1 minus negative 6, giving us negative 7. Okay, so we use our formula for distance for 2 parallel lines or a line and a plane, or a line and a point in 3 space. So we're going to find the magnitude of the cross product of the point vector and the direction vector of the line, and then I will find the magnitude of the direction vector, and then we'll be done. Okay, so I'm just going to cross these actually over here. We'll start with that. And the direction vector 0, 1, 1, 0, 1, 1. So we get the vector 8, -2, 2. And then I want to find the magnitude of my direction vector, which will be 0 squared plus 1 squared plus 1 squared. Do I want to reduce 8, -2, 2?
Yeah.
I do.
Wait, no, it's direction. Wait, no, it's a, wait.
I'm actually finding the magnitude of that vector, so do I want to reduce it before I find the magnitude? No, that would not be a good idea, right? Because when I reduce it, it actually changes the magnitude.
But you have to reduce the final answer anyway, so you're reducing that. That's different.
That would be different. That would be like if I'm reducing an individual vector, right? Not the vector that I get from crossing them. Okay, so we're going to find the magnitude. So notice that the other one, when I have the bars on top, it actually means absolute value. But here, since I get a vector from doing the cross product, the bars on top actually mean magnitude. So that's the difference between magnitude and absolute value, right? So 8 squared plus -2 squared plus 2 squared. And then 1 plus 1 is just 2. So we're getting 64 plus 4 plus 4, so root 72. And then we actually can reduce this to 36 and 2. So that gives us 6 root 2 over root 2, which gives us 6 units. 6 root 2 over 2 gives us 6 root 2 over 2. True.
The roots cancel. Okay.
Okay, I just want to point out to you guys, if you had reduced this, it would have been 4, 1, 1, and you would have gotten 16 plus 1 plus 1, and that's 18. So it wouldn't have worked. Like you would have got 9 times 2, and then it would have given you 3 root 2 up here. So that actually doesn't give us the same answer. Okay? When in doubt, if you're not sure if you can reduce something like within a calculation, maybe best just not to reduce it and then just simplify at the end, because you can still get to the same answer, right? So if you just want to remember, like when I'm expressing vector equations of lines and planes to reduce the direction vector, that's totally fine. And then if you don't want to reduce anymore, then you'll just do the process that we did here and reduce it. Okay? So that's it. Mark? For D, you can. Yes, because if this were 0, 2, 2, then I can always reduce a direction vector. So that would be fine. Other questions? Okay, good. So I just kind of looked through and I found some practice questions for you guys.